Hi, my name is Sérgio Ferreira Andrade, and I am here to present the paper, An Approach to Improve Simultaneous Localization and Mapping in Human-Populated Environments. The work was developed by Kevin Ofuente Couque, me, Sérgio Ferreira Andrade, Denis Barrios Aranibal, Judith Cardinali, and José Dias Amado. This work was supported by Fundo Nacional de Desarrollo Científico, Tecnológico y de Innovación Tecnológica, Fundecit, as executive entity of Concitec in the project RUTAS, Robots for Urban Tourist Center Autonomous and Semantic Based. Now, I am going to do a brief contextualization of our work. One task that autonomous mobile robots have to perform in indoor spaces is to construct the map of their environment and report their location and orientation. This process is called Simultaneous Localization and Mapping, SLAM. To do so, robots extract data through their sensors. To solve the SLAM problem, algorithms based on probabilistic filters have been proposed, such as the Kalman filter and the particle filter. These are base methods for the implementation of various classic SLAM algorithms, such as Gmapping, TinySLAM, and IEEE-SLAM. However, in dynamic indoor environments, moving objects induce the SLAM process to collapse or diverge. Moving objects should not be taken into account to generate the map, and the occlusions that they generate should be solved. A few examples of dynamic environments are hospitals, schools, and museums. In this work, we propose a robust and flexible approach for SLAM algorithms to perform better in human-populated environments by integrating a filtering scheme that manages moving and static objects. A classic SLAM algorithm follows the process marked with the green blocks. We extended it with the modules between the perception of scenes and the application for SLAM algorithm, as shown with blue, dark green, and red blocks. The added modules solve the management of the input data and the occlusions generated by dynamic objects. Basically, the schematic of the proposed solution consists in three phases: an initial phase that consists the scene perception, a filtering phase, and the SLAM phase. The scene perception module allows gathering data from the robot sensor. A diagram of an example of this process is shown in this figure. In the diagram, right, left, and front topics are mentioned since the proposal follows the Robot Operating System (ROS) communications protocol, so each topic contains the data of each sensor of the robot. Callback functions are used for the nodes of ROS to obtain the laser data. The adaptation of laser data as input to the filter module comprises the management of the type of messages provided through the sensors to be manipulated. This module translates those messages representing the characteristic of a type of sensor data, such as coordinates, distance, and orientation, so they can be understood and processed later by the filter as appropriate. The segment objects module includes the capacity of discerning and separating static objects and mobile objects. To perform this role, the proposed algorithm uses the RANSAC method. Nevertheless, it can be substituted by any other filter that performs similar. This figure shows the detailed process of this module, but we are going to explain it later. The scene module with only static objects receives the RANSAC filter output data vector, which is basically the filtered data, while the scene module with moving objects only receives the data that will be discarded, since it is not necessary to be included in the environment mapping. Therefore, only the filtered data contained in the scene only with static objects module are published as data to be used later. Since the structure of a robot can contain multiple built-in sensors, we propose a RANSAC method for each sensor. Thus, its performance is improved. This data published through each sensor of a robot have to be joined and its results are sent to SLAM as shown in this figure. In our approach, any classic SLAM algorithm can be integrated. As an example, we take Gmapping, which uses a particle filter. Therefore, each sample estimates both the pose of the robot and the map of the environment, and the resample stage allows the algorithm to reach the most probable estimate. The application of Gmapping algorithm can usually be outlined as shown in this figure. To validate our approach, we performed a battery of tests in a simulated environment consisting of ROS Melodic, Gazebo 9 Simulator, and RVs, which work by default on Ubuntu operating system. We simulated three words which represent different cases that the robot can face in a museum. The first word represents an empty museum where there are no people moving, so the robot only notices pure static objects. The second word represents a museum with people still in the same place and static objects. Static people in the environment are simulated with models of human beings. The third word is a museum with people in motion using objects called agents, which physically take on the appearance of rectangular boxes in motion. This word is crucial as it allows testing Gmap divergence in dynamic environments. We simulate the Pepper robot since it's a robot that can be used in social environments due to its architecture, which is perfectly suited to analyze land behavior in crowded environments. This is how the Pepper robot looks in the simulated environment. This robot contains three laser sensors in parallel at the base of its lower body, which provides the necessary data from the environment. After configuring the parameters of Gmapping, the generation of the first word map can be visualized in this figure. The generation of the second word map is shown in the left. The difference between this figure and the previous one is that the second shows static people who were recognized by the laser sensor and they can be clearly appreciated in the construction of the map like black dots. The generation of a third word map applying the Gmap algorithm with the configured parameters is shown in the right. This map of the third word shows how the Gmapping algorithm diverges when building a crowded and dynamic environment map. In this image, we can see black dots reflected in the white spaces between the walls. There are people who circulate in the environment. Gmapping uses a scan matching algorithm called ICP that does not fail when receiving only inliners. However, when it receives mixed data, inliners and outliers, the ICP method performance degrades and generates disturbances on the Gmapping algorithm. For this reason, we consider to include a filtering step before entering the slim process. For these experiments, we implement the RANSAC algorithm as the filter executed before performing Gmap. The RANSAC algorithm is implemented to return a mathematical model that it considers sufficient to discern the inliners and the outliers point. Points considered inliners are static objects, and outliers are dynamic objects or people moving the environment. To illustrate the example of how the RANSAC algorithm works, we have here a set of dots from the laser point cloud data. In order to find the best model, at first the RANSAC algorithm generates several curves. The curve with the best score is the chosen one. This score is calculated using a threshold and using it to count the number of the closest points that the model has. Finally, RANSAC finds the model with the highest score or the closest objects. For the specific case shown in this figure, the algorithm chooses the model that best fits and distinguishes between static and dynamic objects. At the end of this process, we have the filtered data from the frontal laser point cloud that RANSAC model has declared as inliners. Now we can see the result obtained with our approach for the third world map. Compared with the map generated with Gmapping without filtering, the improvements are visually obvious. The dynamic objects plotted with our approach are around 20% less than the ones generated with Gmap without filtering. Nevertheless, the static parts of the environment are much better appreciated with our approach, reaching an improvement up to 80% compared with the classical Gmapping. So, we proposed an approach to improve SLAM solutions for dynamic environments with three phases: initial, filtering, and classic SLAM phase. Through this approach, with this configuration, an improvement was obtained in the construction of the dynamic environment map. Another important contribution of the present work is that the second and the third phases are interchangeable. To illustrate our approach, in the second phase we use RANSAC algorithm and the third phase we use Gmapping algorithm. The filtering technique can be replaced by another, such as convolution, and the classic SLAM can also be replaced by another, such as Hector SLAM or Time SLAM. As future work, quantitative results of the error of different approaches will be obtained. Thank you very much for your attention. If you have any questions, you can do it now or contact us via email.